When we worked in the base 10 system, we saw that we could group the balls in or the numbers in piles of 10. So we had 1, 10, 100, 1000, and so on. But it's not the only way to group the numbers in this way. So instead of piling up in piles of 10, so let's put them back like we had from the beginning. So we had 1, 2, 3, 4, 5, 6, and we continue in this fashion to fill up. But instead of grouping in a group of 10, we could group them in any other number we like. For example, if we want to group them in groups of 6. So if I instead pile them in groups of 6, we will have the following instead. So 1, 2, 3, 4. For example, I pile them this way. So when we make a full ring, we have what we call 6. So this is what we previously called 6. And then we start again with new pile with 7. But since we now work not in the same piles as here, when we came to the full 10 pile, we call that 10. But now instead we are filling piles of 6. So when we come to 6, we don't call it 6 anymore. We call it, we have one of these piles and 0 singles. So now this is now a new 10. So we have one of these piles and 0 singles. And this is now called 11. Because we have one of these piles and one single. So this if we work, you say, in another base. So here we work in base 6. And here we work in base 10. We could of course write like this, but you see it's confusing to write 10 because we also work in 10 when they have base 6. So what we really should say is base A, or say it in letters 10. So everything apart from that, we can just continue exactly as we did before. There was nothing special when making this kind of pattern with these balls of 10. We could just as well use patterns here with balls of 6 and call that 10. So there's nothing special about what we call normally 10, because you could use another base and it will still call it 10. So for this guy here, for example, if we assume he's an alien working doing mathematics in the same way as we are doing, but the difference is he only got 6 fingers. We happen to be born with 10 fingers, so 2 more on each hand. But if this guy instead would have done mathematics, he instead would have worked in base 6, and he will call 6 for 10. So for his fingers here we will calculate 1, 2, 3, 4, 5, 10. So for him, his last finger would have been 10, just for us, as our last finger is 10. So there's nothing special with our 10. If you had 6 fingers instead, we would call that 10 instead. So we could just as well work in another basis, for example in base 6. Or if we use other bases, which could look similarly. For example, if we instead been working in base 5, we could have been grouping our balls into groups of 5 instead. And then we would call this 1. We would call this 10. We would call this 100. And we would call this 1000. And this is just as legitimate as doing in any other base. For example, if we choose another base. So for example, in base 2, we would have instead groups of 2. So this is our 1, and then is our 10. This is our 100. This is our 1000, and 10,000, 100,000, and so on. So for example, if we were working in bacteria. And this is how computers work. Computers work in base 2. So for 10 for computer is this, 100 for computer is this, and so on. And for example, in base 2, you only use the digits 0 and 1. So in base 2, you don't use 2 or 3 or higher. You only work with these 2. And it's the same in other bases. Base 6 again, for example. In base 6, you are represented, we grouped them in some different way here. and they have different colors, but it doesn't matter. So in base 6, again this is with 1, 10, 100, 1000. And in base 6 we only use the digits 0, 1, 2, 3, 4, 5. So you can't, in base 6 you can't write an expression like 67 or 60, because it doesn't exist in base 6. In the same way, in base 10, if you work in base 10, you can't write A. You don't use the digit for 10 in base 10. You use 1, 0 for A instead. So you have to keep that in mind. You only work with digits lower than the base. The point of taking up other bases than 10 here is not like we want to understand how computers work and things like that, even though that could be interesting in itself. The point here is more from a didactic perspective. For when pupils learn to calculate in base 10, they learn of course in normal base 10. But for us who has gotten used to learning things in base 10, all the things we once thought was difficult and new, it's hard for us to unlearn what we have learned. So it's a good idea to start for us as teacher student to work in another base than 10. By doing so we can get an understanding of the difficulties that pupils have when they try to learn things from scratch. So we have a chance to see it from their perspective and also have a better understanding how it works ourselves, since if we are forced to work in another basis. Because everything it works exactly in the same way using another basis. The only thing that is different is that we have other digits. And also we won't have the normal multiplication tables and addition tables. We have some other tables to work with. But other than that, in principle it's the same, working in another basis. So now we will see how it works to do math in another basis. For example, if we would like to do calculate in another base, for example base 5. Then we need to remember in base 5, and then it's often good to write the base here, since if we're not working in our normal base, it's good to have a reminder what base we're working in. So 10 in base 5 doesn't mean our normal 10, it means 5. So in base 5 is written as 10. And for example 11 in base 5, that's 6. And for example if you have 1, 5, but that's not possible in base 5. So if you have 2, 0 in base 5, what is that equal to? That means we have two groups of 5. So that's 10. So this is our normal 10. So not to confuse, we could write 10 here is our normal base 10. So if working base 5, we have to keep these things in mind. Other than that, everything works the same way. So for example, if I want to write a number, I can write it like in a positional system. For example, 1, 2, 3, 4, 1234. How much is that if it's written in base 5? In base 5, this means I have 1 over 1000, and I have 2 of 100, and I have 3 of 10, and I have 4 single ones. So how much is this? And here I should write 5, but I just write F to keep it simple. Okay, so how much is 10, 100 and 1000 in base 5? And then we have to remember that 1000, that means 10 to the power of third. And 100 means 10 to the power of second. And this means 10 to the power of 1, but we don't have to write that. So if I now want to translate this to base 10, our normal 10, then I can write 10 here now is 5. So 5 to the power of 3. Then it's 2 to the 5 to the power of 2. And 3 times 5 and 4. So this is 125. 25 times 2, 50. Plus 15 plus 4. So this is 65, 194. So in our normal base 10, 194 is in base 5 written as 1, 2, 3, 4. But we see the logic otherwise is the same. So if we have a number in base 5, we can write the number in our normal base 10. So how do we go in the opposite direction? So for example, you start in base 10, how can I write in another basis? So for example, 300 in our normal base 10. Of course I could write 10 here now, but if I don't write anything at the moment, I mean the normal base 10. So what is 300 in normal base 10 if I want to write it in base 6, for example? Then we have to see how many powers of 6 can we go up to. 6 to the power of 1, yeah, that is 6 of course. 6 to the power of 2, that's 36. 6 to the power of 3, that's 216. So we see that the next one, that will be too much. Because if I multiply this by 6, it's 1296. So I can't go this high. So I have to have at least one of these. 1 6/3. So 216. How much do I have left then? Okay, so if I take away 216, then I have 84. Okay, so how many 6 to the power 2 can I fit into this? 2 of these. If I take 2 times 36, that's 72. So I can have 2 of 6 to the power 2, because then I get 72. And how much do I have left then? 12. And how many 6's, 6 to the power 1, can I fit into 12? It's 2. Because 2 times 6 is 12. And then I don't have anything left. So I don't have to add any singles. So we see here now that this can be written as 1 times, and 6 here now is 10 in base 6. So this is to the power of 3. And then 2 times 6 again is 10 to the power of 2. And then we have 2 to the times 10. And then 0. So in base 6, this is 1, 2, 2, 0. We just read off the digits here. So we see that 300 in our normal base 10 in base 6 is written as 1220. So you see we only have digits between 0 and 5 here. So now we want to learn how to calculate in base 6. Why base 6? Yeah, that's just an example. So for the rest of the calculations now we work in base 6. We'll say a little bit later on some other bases that can have some complications with it. But for now, for the most part, we will stick to base 6 just to keep it simple, not changing base all the time. So we want to learn how to calculate in base 6 because that will give us an understanding from the perspective of pupils how it is for them to start to learn to calculate in the first place. So what this will be as new to us as working in base 10 will be new to pupils. So this will give us a good understanding. So how do you calculate in base 6? Yeah, of course, it's nothing in principle the difference, but in base 6, you can think of that you only have 3 fingers on each hand. So you could start again to calculate on your fingers. So if you calculate on the fingers, how would you calculate then? You would calculate 1, 2, 3, 4, 5, but you wouldn't say 6, you would say 10 here. Then you could continue 11, 12, 13, 14, 15, and 20. So this is how you would calculate if you only had 3 fingers on each hand. So you can start to calculate on the fingers using using your hands, just like kids do work and count on the fingers. So just do in the similar way, just count out loud when you calculate the fingers. But you have to remember that after 5 comes 10, not 6. But after a while you want to get started to be a little bit more sophisticated. So you want to use a number line. So a number line, you put the numbers here, 0, 1, 2, 3, 4, 5, and then you come to 10. That's the 6. And now the point is, one shouldn't transform back to our normal base 10. When doing this calculation, it's very tempting just to change everything back, think you back your head in base normal 10. Do the calculations there and go back to this base 6. But that's a little bit cheating, because if you look at kids, they don't have another base they can go to and learn things. They have to stick with base 10. Same way we should stick with base 6. So we don't cheat and go to another basis and think there instead. So all the calculations should be done without transforming to base normal 10, because otherwise the point is a little bit lost. Okay, so we just start to write up the number line. We can just go as far as we like. So for example, if I want to calculate 3 plus 4. So remember now that we're always in base 6. So I don't write 6 below because it's implicit. So we can just write it up here if we want to remind ourselves. So 3 plus 4, how do we do that? Yeah, we can jump on the number line. You see 3, then we start here. And then you should jump 4 steps. And then we end up here. So you see that this is equal to 11. And of course we can also do subtraction. For example, what is 13 minus 5? Then if I start at 13, and then I should jump 5 steps back, then I see I end up at 4. So this, for simple calculations, it can be useful to do the number line. However, if you go to bases larger than 10, it can sometimes be a little bit tricky. So let us just for a moment go to another base than 6. So let's go to base, for example, base F. What do I mean by base F? Then we have to remember that A, B, C, D, E, F. That's the digits for our normal 10, 11, 12, 13, 14, 15. So this is base 15. Base 15. So let's go to base 15 for a while, because just to see that how does it work if we have some base larger than 10, because sometimes that can be feel a bit tricky. So how will we do a calculation in base F? Remember now that in base 15 we only use the digits 1, 0, 1, 2 up to 9, but then it comes to A, B, C, D, E, and then we don't have F because that's 10 now. In base F it's 10. So for example now, if I want to do an addition like this, what is B plus E? That maybe seem strange, but B, you have to remember that is our, used to be 11 for us. And E, what is that? That's 10, 11, 12, 13, 14. So in our old way of working, this was 11 plus 14. So we know, of course, it's 25 in a normal basis. But we shouldn't do this now in a normal basis of 10. We should stick to the base 15 without changing bases. Otherwise, we lose the point of doing this. So how could you do this addition without cheating and go back to base 10? Yeah, you could start with drawing the number line. So if you draw a number line here, so we start, and now I will skip ahead in the video just to save, so you don't have to watch me writing all this. Having drawn the number line here now, just to say some things first here, we see 9, after 9 is A, B, C, D, E, then 10, 11, 12, up to 19. Then after 19 is 1A, 1B, 1C, 1D, 1E, then it's 20. So you continue in this fashion. So what we want to do now, if we want to add B plus E, that means that we will start here in B. But then we need to keep track of how many steps we are taking. We want to take E steps. So we could of course write 1, 2, 3, and when we come to E. But we see that we almost have to keep in mind 2 number lines. So instead of having jumping on the first one, it could be a good idea to have a second number line to work with. So let us now, we want to go E steps from here. So if we take the first and second number line and move it so that when it starts at B, then we can see directly how far we should go. Now we see, of course, a problem directly. You should have, if I draw it more carefully, I should have equidistant between each point here now. So it's, if I would have had that, yeah, I could read off it directly as compare here. For E, I go up. But now it's not so sure it turned out correctly because I haven't made it that carefully. But if I would have been equidistant, I just have to go up here and read off. And we'll see that B plus E, working E steps here, is 19. But let's check if it's the same. So we pair them together. So you see here, if I pair them together, it didn't work out exactly as I hoped, because this one becomes 1A, not this one, because we don't have the same distance. So you see that this must be equal to 1A. So in base F, base 15, our normal 15, B plus E equal to 1A. So we see here we have the help of using 2 number lines. And that's good to use when we have bases larger than 10. Because then we need, it's good to have to check, because otherwise it could be a bit tricky. But we could, of course, like I've done here, calculate jumping on the line. But then I have to keep in mind the second number line in my head. But having talked about a little bit about the difficulties with base larger than 10, let's go back to our base 6 and work with that. So how will we do that? Now, let's take another example. We have seen for small numbers, we could use calculate on fingers or use the number line. But we can also use something sometimes called among pupils also in school, called 10 pals. Or 10 friends, or whatever you like to call it. So it's not a pen pal, but it's a 10 pal. So a 10 pal, for example, in the normal base 10, we have that, for example, 6 plus 4 makes 10. And we have 5 plus 5 make 10. So these are 10 pals in our normal base 10. In base 6, we have that 1 plus 5 equals 10. So in base 6. And then 2 plus 4 also makes 10. And 3 plus 3 makes 10. So in base 6 we have these three 10 pals. And 1 and 5, 2 and 4, 3 and 3. So whenever we see a 2 and 4 we can group them together to make 10. And that can sometimes simplify our calculations. For example, so now we're working in base 6. For example, if I want to add 3 plus 4, okay, it's simple. So I could of course use the fingers or number line, but here it's also easy to, if I have learned the 10 pals. And this, after a while you have calculated, maybe jumping on the number line for a while, then you start to see these patterns, like pupils also do in normal base 10. So here you see that you can write this as 4, you can write as 3 plus 1. And here we can use associativity, and you can add these two. So you see these two makes 10. And adding 10 and 1 is very simple, it just makes 11. So in base 6 it makes 11. Of course we can, if we cheat for a moment, we see that this is 6 and this is 1, so 6 plus 1 is 7. It should be, so it's correct. But we shouldn't have to be, go back to cheat and go back to normal base 10. Another example. If I add these three, for example, still working in base 6, then we could write like this. The 3 we could write as 1 plus 2. This 3 we can write as 1 plus 2. And 4 here we keep. Because now these two are a 10 pal, and these two are also 10 pal. So we can write this as 5 plus 1. We group these two first, and then we group the two last. So this will be 10 plus 10. So this is 20. Okay, so this is how we can use 10 pals. Let's take one final example. 14, for example. We know that 4 plus 2 makes 10. So we write 5 as 2 plus 3. And 4 plus 2, that's 10. But now we have 1 here also, so this must be 20. So these two must be 20. This is 23 in base 6. An important point to keep in mind when working another basis is that the normal things we're doing with tens, for example, if I have 10 plus 10, then in our normal base we make 20. But this is not something special for our base 10. This also works in base 6. Also in base 6, 10 plus 10 is equal to 20, because 1 plus 1 is equal to 2, also in base 6. Of course, a little bit different to write 30 plus 30. What is that? Yeah, in normal base 10, this is 60, of course. We just add 3 and 3. But in base 6, then 3 plus 3, there are 10 pals, so there are 10. And you have an extra 0 at the end, so this will make 100. So 3 plus 3 is 10, plus a 0 at the end. So you see that the normal rules apply, that we just, if I have zeros, for example, if I would have 300 plus 300, 3 plus 3 is 10 in base 6, and then adding 2 zeros. So the same rules works here, that I should, if I have the numbers end with zeros, I should just add them to the end. But I have to keep in mind that the normal addition don't work the same way as in our normal base 10. So we have another addition table for base 6 and any other base. And for example, if I have 400 plus 500 in base 6, we have 4 plus 5. What is that in base 6? Yeah, we know that 4 plus 2 is 10. So this is 13 in base 6. So this is 13, and then we just put the 2 zeros at the end. So this is how we do it in a normal base 10, and this also works in any other base. So this, if a number ends with zeros, they just add it at the end. So we can do single digit calculations and then add zeros at the end. So that's an advantage we can use. It works in any basis. Let us now come to multiplication, because now I have seen how we can do addition and subtraction. For example, if I'm still working in base 6, how can I calculate 3 times 5 in base 6? And again, without cheating. So of course we know that in base 10 is 15 and we're going to work, but we're not allowed to cheat in that way. So how do we do then in base 6 without cheating? Yeah, we can use the definition of multiplication. We know it's repeated addition. So this means adding 5 to itself 3 times. And now we could add them pairwise. For example, 5 plus 5. That we can do in normal fashion. We know that 5 plus 1, that's 10 pal, so that's 10. So then I had left with 4, so this must be 14. So this is 14 plus 5. 4 plus 5, what is that in base 6? 4 plus 2, that's 10. And then I have additionally 3. So this will become 23. So in base 6, 3 times 5 is 23. So what we have to do it like this, in this way, at least to start with. Then we can start to make a multiplication table. Because have we done this once, it's tedious to do it like this every time. Then we can start to memorize these single digit multiplications. So if you write a multiplication table, then we can write the numbers, the digits here. 0 and 1 we don't have to write because it's so simple. But we start at 2. So we have 2, 3, 4, and 5. In base 6, these are only interesting in the digits we have in our multiplication table. Then we can start to fill in our multiplication table. So for example here now, 3 times 5. So now we know it's 23. So next time we come across that, we can remember 23. This is how we do in normal base 10 also. In the normal base 10 we know that this is 15. We don't do like this or count on figure every time. We memorize 15. In the same way, after a while we start to memorize 23. You don't have to do it actively. After a while you will do it, remember, even if you don't want to remember it. And we also know that multiplication is commutative, so we can write 23 here also. Okay, so we can start to fill up our multiplication table like that. And after a while we really need this table to do calculations efficiently in other bases. And this is just works for pupils also. For pupils to do multiplications, they need to learn this, not calculate on their fingers, for example. So, how can I calculate other things? For example, 30 times 500. Yeah, here we have it again. There's nothing special about base 10. In base 10, how we do? We say this is 15 and we add 3 zeros. It works the same way here. We take 3 times 5, 23. And we add 3 zeros. So this works in base 6, and it works in any other bases. So this rule of thumb, just do the single digit multiplication and adding zeros, works in any basis. Because there's nothing special without 10 bases. It works generally. And we can show that it works. Let's show that it works doing it explicitly. So we just have to remember that, okay, let's take away this because we don't know it that yet. So let's see if we can show it like that, doing it carefully without using the rule of thumb. Then we know that this is 3 times 10 plus 0. In our positional system, this can be written like that. And this is 5 times 100, or even better, 10 to the power 2. And then we have 0, 10, 0. So these remaining zeros here is not so interesting. So you can just simplify it and write it like this. And now we know that multiplication is commutative and associative, so we can change the order here in the way we like. So I can write this as 3 times 5, 10, 10 to the second. And this now, here is a 1. So now we know the rule for adding, if we have powers, exponents, we just add these two because we have the same number down, same base. So we have 10 to power 3, so 1 plus 2. And now we know from the multiplication table that 3 times 5 is 23. Like that. So how can we now go back and write this as a digit combination? Yeah, we just have to add some zeros to the end. We can write this, we just add on some zeros here. It doesn't change the value of the number. Because if I add these zeros, I haven't changed the value. But now I've written it in the way that you see that this is just, per definition, this now means this. This is just a shorthand for this expression if you use in the base system, positional system. So 2, 3, and you see the digit 0 is 0, 0, 0. And then we have come to this. So you see that this works in this basis also. It works in any base. I haven't even used that it's base 6 here. So you see that it would have worked in any base. So you see that we have a rule of thumb, just adding on zeros in the end and doing the single digit calculation. Okay, so let us finally come to division. If you want to do division, it's a good idea to remember that division is can be defined from multiplication. So this number here, the quotient, that's the number you should put here to make this work. So you see that division is defined from multiplication. So for definition, this is the number you should put here. So let's say, for example, you want to do 23 divided by 5. And now we want to do it in base 6 again. So how can we do that? Yeah, what you normally do, you try some numbers, see if it works. That's actually how you do it in normal 10. You try, but sometimes you remember your quotients. So now we want to find a number that should stand here, so to make this work. We see directly, of course, 1 doesn't work. Does 2 work? 2 times 5, what is 2 times 5? Okay, you could have cheated and say it's 10 in normal basis, but we're not allowed to cheat. So this means 5 plus 5. And 5 plus 1 is a 10 pal, so this is 10 plus 4, so it's 14. So it doesn't, so it's too small. And then take the next one then. You take 3. So that's 5 plus 5 plus 5. This was 14. And this 5 plus 4. 4 plus 5, what is that? 4 plus 2 is 10. So 4 plus, that's 13. And then we had 1, so it's 23. So we see now that we end up with this. So this is 3. So after trial and error, we see that we have come to the quotient 3. So this is how you can how you do divisions. So this works. Actually, you have to do like this. You have to test and try backwards with multiplication. So this is a bit tedious, but for small numbers, this is a way to go. Then after a while, of course, if you have come across this many times, you remember that 23 divided by 5 is 3 in base 6. You can also use 10 pals for multiplications. 10 pals for addition are not the same pals as for multiplication. So for example, if we take if we go normal base 10 now for a while, we have, for example, if you want to calculate 5 times 18, how will you do that in normal base 10? There are different ways you can do this in mental calculation. But for example, you can multiply 5 by 2 and at the same time divide 18 by 2. Because now this is 10 and this is 9, so this is 90. And you see here we have used that 5 and 2 are 10 pals when it comes to multiplication. And you can do in the same way for other bases. You just have to use other tenths. And it's not the same tenths as for addition. For example, 3 times 14 in base 6. What is that? And then you have to remember or have seen some time before that 3 times 2 is a tenth or tenths. So you have to remember that 3 times 2, because that is, you could just as well write it as 2 times 3. This is 3 plus 3. And 3 plus 3, that's a tenth in addition. So this is 10. So if you remember that 3 times 2 is a tenth, then you can multiply this by 2, divide this by 2. So this becomes 10. And this become 14. How do you know that in base 6? And then you have to do the same again. 14 divided by 2. That's the number you should multiply 2 by to get 14. 1 is too small, so you have to try. Okay, 1 didn't work. You have to try 2. 2 times 2, that's 4. It didn't work. 2 times 3. Okay, but we see, so here that was 10. It doesn't work. 4 then. Okay, we see that 2 times 3, that was 10. And if we do one more, 2 times 4, that means basically just adding one more 2. You see it, 2 times 3 is 10. 2 times 4, that's adding one more 2, so this is 12. And 2 times 5, that is 14. So we see that after a while you have tried, you have to end up with 5 here. Or you could just remember by heart. Just as we remember by heart that 18 divided by 2 is 9. For how do you know that in base 10? You have learned it by heart. Or you have tried it in the hard way from the beginning. So here you have, this should be equal to 5. 10 times 5. Now we can use this rule of thumb. So this is just a 5 and adding a 0. So in base 6 we have that 3 times 14 is 50. And then we have used the tenths here. But you see in the beginning when you're starting to learn things is quite a lot of work. The reason this seems simple is because we have gotten so used to it. Because we know that 5 and 10 are tenths, and we know that 18 and 2 is divided by 2 is 9. But from the beginning we had to learn this, and we had to do like this hard way. So that's one of the points of learning this, is because you see it from the perspective of the pupils. This is not so simple for them as it maybe is for you. Of course, now they have learned some multiplication perhaps before they go to school, but in principle, they have to learn it like that. As we have seen, after a while doing all these calculations can be tedious. So after a while you should start to memorize your multiplication and addition tables. You should have all the additions for the single digits, for example 2 plus 3. You should remember that it's 5. Or you have 4 plus 3. You know, you have learned by heart now that this is 11. Or for once, you know that 4 plus 2 is a tenth, so it's 11. So if you want to do efficiently, after a while you start to memorize your multiplication and addition tables. And minus, of course, if you want to subtraction, you can use your table backwards. For example, if I want to do 11 minus 4, then I know that this is 11. I know 3 plus 4 is 11. So I know that 11 minus 4 is 3. So you can also use addition table to do subtraction. In the same way as we used multiplication to learn divisions. Okay, so after a while you should start to memorize your multiplication tables. And then you start to come to even larger calculations. So for example, if I want to do addition like this, and now we are still working in base 6. So in base 6, how do I do this? Now it's not practical, efficient to do number lines, and you don't have any arithmetic results from a table. So you need to do the algorithms. And we have already seen the algorithms for our normal base 10. And nowhere in those algorithms were there any special use of base 10. Because all those works in any base. So all those algorithms we saw before works in any base. The only difference is that we have to memorize other multiplication tables and addition tables. So the addition tables and multiplication tables are not the same in base 6 as in base 10. So if we memorize these two, then the rest here will just be exactly the same as in base 10. And this will be the case for whatever base we work in. So instead of like going through all from the beginning again algorithms, we all do the same algorithms. So let's do this, for example, in addition algorithm. So now we have to assume that we have learned by heart these addition tables. So then we do 2 plus 4. Yeah, we know for after a while we know this is 10 in base 6. Then we write like this. This one group here we move to that, just as we did for normal base 10. We exchange up. 1 plus 5, that's 10, plus 1, so this is 11. And 1 plus 3, that's 4. And 3 plus 4, we know that 4 plus 2 is 10, so this is 11. So this is exactly the same way as we did for our normal base 10. That's just that we use another addition table. And the same way, for example, if I want to do a subtraction, then I do the same way. 1 minus 2, that's not possible, so I have to exchange 1 from there. I take 1 from there, I have 10. Remember now that each of these represents 10. So 11 minus 2. Then I have to remember this table here. Here I have 2, and somewhere in the table I have 11. Then I have to remember that number that corresponds to that. That's 11 minus 2. 11 minus 2, that number up there. And what should 11 minus 2 be? Yeah, we can also do it in the number line. If I have 11, then we have 10. Then we have 5, base 6. So 11 minus 2, we should jump 2 steps. So we come to 5 here. So 11 minus 2 is 5. Now we have 3 minus 5. Again, we have to exchange. 13. Again, I can use here, but I haven't filled it in, so let me do it here. 13 minus 5. So it's 1, 2, 3, 4, 5. Then I jump to 4. And then I have 1 minus 4. Again, I have to exchange. 11 minus 4. 1, 2, 3, 4. Then up at 3. And 4 minus 3 is 1. So you see that the pattern and logic is exactly the same as other bases, but you just have to keep in mind all the single digit operations give different results than from normal base 10. So let's do examples also for multiplication and for division. For example, if I want to do this now, 2 times 4. Now I do the same way as I did before. 2 times 4, what is that? Yeah, then I have to know the table here. I have to have this remember. And 2 times 4 is 4 plus 4. So this is 12 in base 6. So write like this. 2 times 1 plus 1, that's 3. 2 times 2, yeah, that's 4. 3 times 4, what is that? That's 4 plus 4 plus 4. So it's 12 plus 4 more. So that's 20. So I need to 0 there and 20 here. Well, 2 there. 3 times 1, that's, and then I get 5. 3 times 2 is 6. And then the final row, 5 times 4. So 5 times 4. Okay, what is that? Then I have 4, 5 times 4. Again, normally you should use here now the table, but I haven't filled it in. So when you start to do it, you shouldn't have able to do it. You just look at the table. But now I haven't filled it in, so I have to do that first. So 4 times 5, that's 5 plus 5 plus 5 plus 5. 5 plus 1, that's 10. So this is 10 plus 4, the 14, and this is 14. So I have 10, 10, that's 2. 4 plus 4, what is that? That's 12. So I need to end up with the 3, 2. So this you have to do in the way you learned before. So you get this 32. So 5 times 4 is 32. 5 times 1 plus 3, that's 12. And this is 5 times 2, what is that? 5 plus 5, that's 14, plus 1, 15. So this is 2, 3. 4 plus 2 is 10, pal. So that's 10 plus 5, so this is 15. I've written 6 here, I shouldn't write 6. So that's a mistake. 6 is of course 10. Why did I write 6? Was because of 5 times 4 or... No, it was 3 times, 3 times 2, that's 10. These are 10 pals, so this should be written 10 here. So this is 3, and this is 10, so this is 2. So this is the answer, 203,532, if you multiply these two. And finally, let's do a division, just to see how that works also, but the principle is the same. So let us do division, this division. So now we have to try to see how many times do 12 go in 3. Yeah, we know that this, we haven't had about the first row, we know that this becomes 0. So let's go directly to 32. How many times do 12 go in 32? In base 6, of course. Okay, 12 times 1, that's 12. 12 times 2, what's that? That's 12 plus 12. And 12 plus 12, that's 24. That's too small. So if you add one more, that is, if you take 12 times 3, you add one more 12. Then this is 10. This is 4. Was that right? No, that wasn't right. Or was it? Yeah, that's right. So I can only go 2 steps. So I can only do 2 times. So 2 times 12, that is 24. But 3 times I can do. So 2 times that's 24. So I can put 24 here. Okay, so I have 12 people, and each person can get 2. Then I'll do the subtraction here. Don't have to exchange, but okay. So this is 10, 12 minus 4. 12 minus 4, 12 minus 2 is 10, and 2 more, then I get to 4. So this is 4. And then I need to take down this one. Then I have to try again. How many times do 12 go in 44? But now I know that this works, and the next one will must be too large. Because how much is that? I should add another 12. So this is 52. So I can do this 3 times. So 3 times 12, that is 40. So this is 4. And then I take down 40. But now I know that this is 40, so now another 3. 3 times 12 is 40 again. Now this is 0, I don't have any digits left, so this is the final answer. Of course, if it would have been something else than 0, and we had our last digit, then we would have some remainder. Let me finish off this lecture just by saying some final comments. So now we're seeing how we can do calculations. So there's nothing special with our normal base 10. We can calculate in any base. And the same holds when we come to decimal numbers and things like that. But for example, going ahead, because we haven't talked about decimal numbers for a normal base 10 yet, but For example, if you can write decimal numbers in other base. For example, in the normal base 10, if I have 1.234 and multiply by 100, we know that we just have to move these 2 steps. If you're working decimal numbers in other bases, the same thing will hold also there. So all these memory rules holds in all bases. And things like this, for example, 0.01 times 0.1. In our normal base 10, this is 0, 0, 1. We just have to see how many decimals we have. This is a memory rule we use in base 10. But there's nothing special here about base 10. This works in any base. So this I don't even have to write what kind of base I'm working here. So the memory rule works also here. And a lot of other things, for example, I have 1000 divided by 100. In our normal base 10, you just shorten out zeros and get 10. This works in any base. Of course, things like this you should prove, but it works in any base. So all these rules are not that it's very special about our base 10. It's very convenient. This happens in any base. And then there's also some advantages to use some bases in some situations and other in others. For example, one can start to think in the normal base 10. In the normal base 10, 1/3 is written in a decimal form like this. Then we can start to think that there's something special about the 1/3 because you give infinitely many decimals. But if we would have instead calculated in base 3, in this base, then 1/3 in base 3 would have been written 0.1. Only finite number of decimals. We haven't really talked about decimal numbers yet, but things like that will happen. And also things like, for example, percent in base 3, or in a base 6. So you have a base 6. How much is 50% there? Then you don't talk about 50% anymore. In base 6, 50% corresponds to 30%, because 30% plus 30% in base 6, that's 100%. Because in base 6, 3 plus 3 is 10. So in other bases, you don't talk about 50-50 more. If you're in base 6, you will be able to talk about 30-30. Then you have things like divisibility, for example. In some bases, you just look at, in a normal base 10, you look at the last number. If it ends with a 5 or 0, you know that it's divisible by 5. You have other rules for other bases. But so some things change from base to base. For example, this if it's a finite number of decimals or infinite number, 30-30. But some other things don't change. No matter what base you work in, all the rules of calculation works the same way. For example, this distributive rule. This works exactly the same way in all bases. It has nothing to do with base. So this works the same in all bases. And also, for example, you take a number like pi. Pi is, in any base, it's always an irrational number. So you can't write it as a fraction of integers in any base. So that's irrespective of that. But of course, if you would have been writing it as digits in our normal base 10, it is like this. But in other bases, it will be other digits. So if you've been working in base 6, it wouldn't be 3, 1, 4, it would be some other digits. But still, it will be infinite many digits and no sequence that will repeat itself. So sometimes some things change when you change bases, but other things do not change.